Welcome back, everybody. This is Dr. Gallenstein, and I'm here again for another lecture in advanced microeconomics. Today's lecture is following up on the lectures on the topic of utility maximization, but in this case, what we're going to do is we're going to look at kind of the inverse problem, or what we might call the dual problem, as I'll explain later, which is what we're going to call expenditure minimization. Expenditure minimization. All right, so that will be the topic of today's lecture. Let's jump right in. So what I want to do, actually, I'm probably just going to... What I'm going to do is I'm going to separate this screen into two halves. And I'm going to show you kind of two sides of the same coin, okay? So first, let's just remember utility maximization. Remember, what we wanted to do is we wanted to find the values of C and B that would maximize our utility subject to a budget constraint. All right, so we wanted to find the values of C and B that maximize our utility subject to our budget constraint. Okay, and so when we do that, and we solve this problem, we get C star and we get B star, and then we take those, we can plug them back into the utility function to get, so utility of C and B, all right, which gives us our indirect utility function. Okay, now in this case, I just want to point out a couple of things. I just want to point out a couple of details here. One is that here we treat I and PC and PB as parameters, right? That means these are given. These are given. They are constant. When we do the utility maximization, they take these things as constant, and then they choose the value of C and B that give them the max amount of utility. Expenditure minimization is kind of the inverse problem. Okay? So here, with utility maximization, we take income as given. Income is given. Income is constant. And then we choose C and B to maximize utility. Expenditure minimization, actually, let me give this a title. All right, this is utility max. Okay, expenditure minimization. Expenditure minimization is the inverse problem. What we're now going to do is we're going to choose C and B that minimize our expenditures. So instead we're going to choose C and B that minimize the expenditures subject to our utility achieving some pre-specified level of utility. Okay, so now you can see that in this case, expenditure minimization takes utility as the constraint, and then people choose C and B to minimize their expenditures. So you can see that they're kind of flipped. Let me just illustrate that. Actually, let's just... All right, just going to delete some of this stuff, make this really clear. Okay, so with utility maximization, we maximize utility subject to a given budget constraint. With expenditure minimization, we do the opposite. In this case, now we are minimizing expenditures. Okay, we're minimizing expenditures. We're choosing C and B such that we spend as little as possible, and then we take the utility as the constraint. That is, we say we want to spend as little as possible such that we're able to achieve a given desired level of utility. So now utility is the constraint, and we are minimizing expenditures. So what's going to happen is we're going to do a minimization problem. We're going to find C star and B star. Then we will take those and we will plug them back into this expenditure function. So this here we might call the direct expenditure function if we wanted to. Let's just label it E of C, and B. All right, so here's the expenditure function. What we're going to do is we're going to take those optimal values, we're going to plug them into the expenditure function, C and B. Okay, and this will be then equal to what we will call the optimal expenditure function. Oops. All right, so then this we call the optimal expenditure function. All right, and over here we call this the indirect utility function. Okay, so what we're going to do is instead we're going to do a minimization problem, find the optimal values, plug them back into the expenditure function, and we're going to get the optimal expenditure function. Now you might notice something. If you're looking carefully, you might notice here that the indirect utility function has I as a parameter, but the expenditure minimization problem, which yields the optimal expenditure function, has utility, has a given utility level as a parameter. This is the only thing that's different between these two. The indirect utility function takes income as a given, takes income as a parameter. The optimal expenditure function takes utility as a parameter. That is, the target utility value as a parameter, as a given. And so that is here, when we do utility maximization, we're going to get C star as a function of the prices and income, C star, B star the same way, prices and income. When we do expenditure minimization, we will get C star as a function of, again, prices, but utility is now a parameter. All right, so now it's no longer income as a parameter, but now it's utility as a parameter. Okay, so basically we have two sides of the same coin. On the utility maximization problem, we take income as a given. We choose C and B to maximize the utility. In the expenditure minimization problem, we take utility as a given, and then we choose C and B to minimize the amount of money we spend, that is, minimize expenditures. Okay, and then we do the same process where we solve for the optimal levels, we plug them back in, and then we have two, we say, kind of inverse or dual expressions. One is the indirect utility function, one is the optimal expenditure function. All right, so that's a little bit of an outline. We're about to do that. Now I want to go a little bit more into detail in terms of the intuition here to help us understand the difference between these two approaches. Okay, so let's move to the next step. Let's do a little bit of intuition. Again, I'm going to split my screen in half. We're going to have utility maximization here, and we're going to have expenditure minimization here. Okay, so in utility maximization, what we do, so let's throw our indifference curves back up here, right? We take the budget constraint as a given. This is our budget constraint. It's given. There's a fixed budget constraint that corresponds to a given level of income. And then what people do, let's use these same colors. If you remember from our lecture, people will choose a bundle that corresponds to the utility that corresponds to the indifference curve that gives them the highest amount of utility. And so basically, what people do is that they will choose the indifference curve that gives them the most utility, subject to the budget line that does not change. This budget line does not change. And so they will choose bundles. They will choose a bundle that gives them the most amount of utility. So they will not choose any bundle on indifference curve 1 because they could do better. They will not choose any bundle on indifference curve 3 because they can't afford it, because the budget line is set, it's fixed, they can't afford anything here. So they will choose a bundle that lies on the utility function that is as far away from the origin as possible, yet still intersects with the budget line. Okay, so they're going to choose this bundle right here. Okay, but what you can see here is with utility maximization, the budget line is fixed. The budget line stays the same. And utility can vary. People will choose the bundle that gives you the most utility given the fixed budget line. Well, expenditure minimization is kind of the opposite problem. With expenditure minimization, the individual will take the indifference curve as a given. Let's say this indifference curve corresponds to some utility value, we'll call it U bar 2. So with the expenditure minimization problem, they will minimize the amount of money that they need to spend to achieve this level of utility. So now the utility level is fixed, and what they will do is they will choose an expenditure level that will allow them to minimize their expenditures. I don't like that. Let's get rid of that. To minimize their expenditures while still achieving. That's not good either. While still achieving the target utility value. Okay. And so now let's use the same intuition. Okay, so now what they're going to do is they're going to choose the expenditure level, the lowest expenditure level possible that will allow them, I still don't like that blue line, that will allow them to achieve the given or the specified level of utility. Oh man. Okay. One more time. All right, that's much better. Excellent. Thanks for your patience. Okay. So now they take the utility value as given, and then they will choose the expenditure level, the lowest possible expenditure level that still allows them to achieve the desired utility. So now let's talk this through. Let's think this out. Okay. Will they choose a bundle that is on this indifference curve, the light blue one? Will they choose a bundle on that indifference curve? Well, the answer would be no. They will not choose any bundle on this not indifference curve, budget line. They will not choose any bundle on this budget line because then they are not achieving the desired level of utility. They would achieve a lower level of utility if they consumed a bundle on this budget line. This budget line does have lower expenditure, but they do not achieve the desired level of utility, so they would not choose it. Would they choose a bundle on the purple budget line? Well, in this case, they could choose a bundle on this purple budget line. For example, they could choose this bundle or this bundle. In either case, they would be able to achieve the desired utility value. However, they would be overpaying. Their expenditures would be too high at this purple budget line. They're spending too much money. The farther out the budget line is, the more money is being spent. They could achieve the same amount of utility by instead choosing this bundle. If they choose this bundle, they are still achieving their desired level of utility, yet they are minimizing the amount of money that they have to spend to achieve it. And so this bundle here will be the optimal according to the expenditure minimization problem. This bundle here would be the optimal according to the utility maximization problem. We'll discuss later how these two might be a little different. But this hopefully will give you some of the intuition. Give you some of the intuition in between in terms of the difference between utility maximization and expenditure minimization. The utility maximization, the utility is allowed to vary, and the budget constraint remains the same. And so you're choosing the bundle that gives you the most utility given a fixed budget constraint. With expenditure minimization, it's the opposite. With expenditure minimization, we're choosing C and B that minimizes the expenditures. That means expenditures are changing given a fixed amount of utility. Okay, so just one last point here. Income is fixed. Income is fixed. Here, utility is fixed. That is, it stays the same. It's held constant. Okay, so there we go. Utility maximization, expenditure minimization. Okay, so then let's do an example of an expenditure minimization problem. All right, I'm just going to delete all of this, and let's do an example of an expenditure minimization problem. So now, expenditure minimization problem is set up in a very similar way. So min, we're going to choose C and B to minimize our expenditures. All right, subject to a constraint, and the constraint is some utility value. Let's call it U star equals some utility function of C and B. All right, and so what we're going to do is, again, we will set up the Lagrangian, and then we'll maximize, or we'll minimize it following the same procedure as we did for utility maximization. Okay, so now, because this is an example, I'm going to go ahead and give us a utility function. It's going to be a new one, but don't be too intimidated. I'm going to say that utility equals the square root of CB. And as a little note over here, the square root of C times B is equal to C to the 1/2 power times B to the 1/2 power. All right, we might find that that's helpful to remember. Okay, so what we'll do is we then go and we set up the Lagrangian, C, B, lambda equals PCC plus PBB, right? So we start here, plus lambda times the constraint, so it's U minus C to the 1/2, B to the 1/2. Okay. All right. So now let's take the derivatives. All right. Derivative with respect to C. All right, let's go term by term. Term by term. What is the derivative of PC with respect to PCC with respect to C? Well, it'll be PC. Okay. What's the derivative of this term with respect to C? 0. And then what's the derivative of this with respect to C? This is where it gets a little bit trickier. All right. Minus lambda. What's the derivative of this with respect to C? Well, it'll be 1/2. All right. B to the 1/2 times C to the negative 1/2. Can you see that? Why don't I come over here and then show? So if we expand this out, it'll be minus lambda C to the 1/2 B to the 1/2. I'm going to take the derivative of this. Well, maybe I'll rearrange it to make it look a little bit easier. b to the 1/2, c to the 1/2. We know from our basic formula, right, our basic formula of a derivative, that if this is the function, then this is the derivative. So let's just use that formula here. Basically, this part is the lowercase a. This is the lowercase a. This here is the b. So let's just plug that in. So what we're going to get is minus lambda, put the b out here, 1/2, okay, b to the 1/2, okay, and now here we go, it's basically 1/2 minus 1, which becomes negative 1/2. Now we could write this a little bit differently if you wanted to. It depends on how you want to express it. You could also express it this way. I'll leave that up to you, what you prefer in terms of how you want to express it. Okay. So there we go. Set that equal to 0, first order condition. Okay. Take the derivative with respect to b. pb minus lambda. The exact same thing. Go through the same procedure here. Except now it's the opposite. Alright, set that equal to 0. Alright. Next, first order condition. Derivative with respect to lambda. So we just get u star minus c to the 1/2 b to the 1/2 equals 0. Alright, as is typical, then what we want to do is we want to take all of these and we want to solve it for c star, b star, and lambda star. All of them in terms of parameters. So let's do that. Now, I'm going to use a little bit of a different strategy when I solve this one. Here what I want to do is I'm going to solve this for lambda, this for lambda. And then I'll show you what I'm going to do next. Okay, so let's solve this for lambda. All right, let's just go step by step. So I'm going to move basically this whole term to the right side. So I'll get PC equals lambda 1/2 b to the 1/2 c to the minus 1/2. Okay. I'm solving this for lambda. So what I'm going to do is I'm going to take lambda equals, and then just divide both sides by this whole expression here. So we'll get PC over 1/2 b to the 1/2 c to the minus 1/2. Okay, now you might prefer to write it in this alternative. You might prefer to simplify it. So let's simplify it. This would be PC divided by square root of b divided by 2 times the square root of c. And then that will become PC, basically 2 PC square root of c divided by square root of b. Okay, quick algebra side note. If I have a divided by b divided by c, that's the same thing as a times c over b. And I just used that rule here. Okay. All right, I'm going to do the same thing over here. I'm going to solve for lambda. All right, lambda equals PB over 1/2 b to the minus 1/2 times c to the 1/2. All right, and then I'm going to simplify it. PB divided by square root of c over 2 times square root of b, which becomes 2 PB square root of b over square root of c. Okay, then what I'm going to do is I'm going to take these expressions and I'm going to solve these expressions for C or B. Either one's fine. I'll solve it for B first. Okay, so this is what I'm going to do, is I'm going to notice that these two things are equal to each other because they both equal lambda. So when I'm going to come down here, all right, I'm going to say 2 PC square root of C over square root of B equals 2 PB square root of B divided by square root of C. All right, these equal each other because they both equal lambda. Well, then let's simplify this. Multiply both sides by square root of C. That will give us 2PCC. All right, equals, multiply both sides by the square root of B. That will give us 2PB times B. Right, square root of B times square root of B is equal to B. Okay, and then I'll notice here that I can just cancel out the 2's. All right, so let's say I'm going to solve it for C. So C equals PB divided by PC times B. All right, are we done? No, we're not finished yet because this still has a variable in it. We need C purely in terms of parameters. Okay, well then where do we go next? How do we solve this? What's the next step? I'm going to have to make some space for it. I'll come up here. Might end up needing to make some more space, but I'm going to try to avoid it. Alright, so let's just... Alright, so I'm going to come up here. What do we do next? We're going to take this, actually I'll use a different color. We're going to take this, and we're going to plug it into the final we're going to plug it into the final first order condition. So what we're going to have there is we're going to have U star minus, plug C in, PB divided by PC times B squared, or to the 1/2, times B to the 1/2 equals 0. All right, now we're going to solve this for B. Let's solve this for B. Now, how do we do that? Well, let's notice this, PB PC to the 1/2 times B to the 1/2. We've just distributed this exponent over multiplication, which we can do. Okay, now notice B to the 1/2 times B to the 1/2 is just B. So it's be U star, U star minus, I'm going to turn this over to square root, it just looks a little prettier. See, all times B equals 0. So then B, what does B equal? Solve that for B. B will equal square root of PC divided by PB times U star. All right, this is all parameters, no variables, so there we go. That is optimal B. Now what we do is we take optimal B and we plug it into the C that we have down here, so let's do that. C equals PB times PC multiplied by square root of PC divided by PB times U star. Okay, and then let's just we'll notice here there's no parameters. That means this is C star, but let's just simplify it. All right, quick aside. Let's rearrange this. So what we're going to have here is we're going to have square root of PC divided by PC times PB divided by square root of PB. Well, what is P square root of PC divided by PC? And what is PB divided by the square root of PB? Well, this would be the same as square root of PB divided by square root of PC. So therefore, what we're going to get here is the square root of PB divided by square root of PC times U star. Okay, so then let me just rewrite it. B star is square root of PC divided by PB. C star is square root of PB divided by PC times U star. These are our expenditure minimizing values. Expenditure minimizing values for B and for C. Okay, so there we go. A little bit of some grueling algebra, but we got it. We got it at the end. That is an example of an expenditure minimization problem. Okay, be sure to follow these steps very carefully. Some of the algebra is complicated. Feel free to come to my office if you need any further help. All right, so what we're going to do now is we're going to keep this. Let's keep that there. I'm going to delete this algebra here. All right, and then I'm just going to show you what it looks like to plug those expenditure, plug those optimal values back into the expenditure function. All right, so if I want the optimized, let's say I want the optimized expenditure function, and what I'm going to do is I'm going to take these values, I'm going to plug them back into the expenditure function. Okay, remember it's PCC plus PBB. All right, now I want the optimized expenditure function. That'll give it to me in terms of just the parameters. So we'll plug this back in. So it'll be PC times square root of PB divided by PC times U star plus PB times square root of PC divided by PB U star. We can simplify this. We'll notice that what we end up getting here is square root of PB PC, because we have aside we have PC divided by square root of PC, which will equal the square root of PC. All right, square root of PC times the square root of PB equals the square root of PC times PB. Okay, U star. All right. U star plus same thing here, PC U star. So then we get 2 PB PC U star. So there we have it. This is the optimized expenditure function using our example. All right. So now what I want to demonstrate, one last thing before we finish this lecture, what I want to demonstrate is I want to demonstrate a concept called duality. So duality is basically going to be, it's going to kind of demonstrate to us how the it's going to demonstrate to us how the utility maximization problem, utility max problem, relates to the expenditure minimization problem. Okay, so I've said that these two are dual problems. That means they're kind of inverse problems. They are both attempts at arriving at the same kind of conclusion, that is, the optimal values, but they're coming at it from different directions. All right, they're going to come at it from different directions. All right, so here's the basic idea. The utility maximization problem is going to result in a value function. and that value function has income as a parameter. This is going to result, I would say value function, indirect utility function, in the optimized expenditure function, which also has prices as parameters, but it has utility instead of income. Well, this is one thing that we will find. That the value function, let's do this. If I take the value function and let me clarify. The value function, or the indirect utility function here, is, let's do this. This is in units of utility. It's in units of utility. This is in units of income. Okay, so this function, this tells us how much utility we derive given these parameters. This function tells us how much we have to spend in order to achieve this level of utility given these parameters. This is how much we're going to spend. This is how much utility we get. And so we could, let's do this. If I take my indirect utility function, take the parameters, and I plugged in my expenditure function, this would give me that optimal utility. This gives me the utility at which the expenditure function assumes the utility that the expenditure function takes as a given. And the inverse is true as well. If I take the expenditure function and I plug in the value function, or the indirect utility function, this will give me an income equal to the amount that the expenditure function would give. That is, this will give me the same amount of income as we assumed in the value function maximization process. So these two things are kind of inversely related to each other. Okay. Now I kind of want to demonstrate this duality relationship, and I want to demonstrate it using the expenditure minimization problem that we already had. So this is what I'm going to do. To demonstrate the duality, what I'm going to do is I'm going to solve a utility maximization problem. I'm going to solve the utility maximization problem that would go with the expenditure minimization problem that I already did. So let me just be clear what I'm going to do here. So we did the expenditure minimization problem where we found C and B that minimized this expenditure function subject to this utility function, right? So we did that, and what we found was C star equals, we found that C star equals the square root of PB over PC times utility, and we found B star equals square root of PC divided by PB U star. We found that, we plugged that back in, and then we found the optimal expenditure function to be 2 PCPB times U star. We found that. Now I want to do the inverse problem. I want to do the utility maximization problem. So I want to do the exact inverse. I want to do this. I want to maximize CV, this utility function, subject to this expenditure function with some given level of income. So I want to do this problem. This is the inverse problem of this expenditure minimization. Then I'm going to show that duality condition that I showed earlier holds to be true. Okay, so let me do this. What I'm going to do, I just want to save these. I'm going to save these up in the upper corner here. Okay. I'm just going to save that. All right, and now I'm going to do this utility maximization problem. All right, so I'm going to maximize this utility function for C and B, subject to this constraint. Okay, so let's do it. We set up the Lagrange. All right, then we take the derivative. Exact same procedure. Okay, and remember, square root of c times b is the same thing as c to the 1/2, b to the 1/2. I think that makes this a little bit easier. So then let's take the derivative of this. That'll be 1/2 c to the negative 1/2 times b to the 1/2 minus lambda pc set it equal to 0, first order condition. Okay. b 1/2 times c to the 1/2 b to the negative 1/2 minus lambda pb equals 0. And then finally, lambda divided by, or L divided by lambda, or the derivative of the Lagrangian divided by the derivative of the Lagrangian with respect to lambda, okay, income minus PCC minus EBB. Okay, then what I'm going to do is I'm going to solve this in the same way that I solved the expenditure minimization problem, and that is I'm going to use the same strategy. Solve both of these for lambda. So I'll do that. So what we have here is we'll have lambda PC equals 1/2 c to the minus 1/2 b to the 1/2. That will give us lambda equals 1/2 c to the minus 1/2 b to the 1/2 divided by pc. Now, just as before, we might prefer to simplify this. I do. So I'm going to simplify this. This is going to simplify to 1. This is going to simplify to b to the, actually, I'm going to write it all the way this way. Square root of b divided by 2 square root of c, all of which is divided by pc. That is going to simplify to square root of b divided by 2 pc square root of c. Okay, so lambda equals that. For the sake of time, I'm going to do that same procedure here to isolate lambda. And lambda is going to be equal to, so from this equation, isolate lambda. Lambda will be equal to the square root of c divided by 2 times pb. So just the inverse of this. All right. Now again, I'm going to take these two, I'm going to set them equal to each other, and I'm going to solve them. I'm going to solve them for c, just like I did before, using the same strategy. All right, so if I multiply both sides by the square root of c, I will get c divided by 2pb. And if I multiply both sides by square root of b at the same time, I will get b divided by 2pc. All right, then simplify that a little bit further. I will get 2pcc equals 2pbb. Solving for c, Canceling out the 2's. Solving for c, I get PB divided by PC times B. With this, I'm going to take this c, I'm going to plug it back into, okay, I'm going to take this, I'm going to plug it into here, and then I'll use that to derive my B star. So let's do that here. Okay, so PC cancels out. See, I switched over to this. I minus PBB minus PBB. All right, let's let's solve this for B. I minus 2 PBB equals 0. Solve that. We're going to get B equals I divided, sorry, we're running out of space. Let's come over here. B equals I divided by 2PB. All right, that is B star. It's B star because it's a function of only parameters and not of variables. If I want to know what C is, I plug B star back into C. Switch back over to black here. Plug that in here, and we'll get C star equals PB divided by PC multiplied by I over 2PB. The PB's cancel out. And we get I divided by 2PC. Okay. So there we have it. We have maximized the utility function that corresponds to the expenditure minimization problem that we did earlier. So that now we have C is I over 2PC, then B star is I over 2PB. Okay, so there we go. We have maximized this utility function. Now what I want to do is erase all of this. Okay, and then I'm going to show that duality condition, and then we'll be done. It's a long lecture. All right, so now let's take these and we'll plug them back into the utility function. Remember, the utility function is the square root of C times P. So we take these, plug them back in. We're going to get the square root of I over 2PC times I over 2PB. Okay, that would equal to the square root of I squared divided by 4PCPB. Okay. Square root of I squared is just I. Square root of 4 is 2. So then we get square root of PCPB. Okay, so then our indirect utility function, is equal to I divided by 2 square root of PCPB. All right, and now we're going to remember that the expenditure minimization problem yielded this. So now if I want to show that duality holds, remember duality, what I said was the value function, the indirect utility function evaluated at the expenditure minimization, the optimal expenditure function is just equal to U star. The expenditure minimization problem, this is evaluated at the utility level of the value function, or the indirect utility function, is equal to I. Okay, so I'm just going to show that this is true, and then we'll be done. So actually, I'm just going to show it for the first one. That should be sufficient. So what I'm going to do is I'm going to take E, and I'm going to plug it in for the I. So V divided by 2 PCPB, and then lo and behold, there we have it. Equals U star. Okay, so there we go. We've just proven, or we've just demonstrated, that this duality condition holds. This expenditure minimization and utility maximization drive these two related expressions. Okay, we're going to go more into detail exactly why we would do both of these, but this will suffice for today. All right, I hope you have a great rest of your day. Thanks for sticking through a long lecture with a lot of algebra. Good luck, and we'll see you in class.